Hello and welcome to this lecture on the scientific process. As we learned in the first 2 weeks of this course, nutrition is very much a science, just like biology or chemistry or physics. And so the way that we learn about nutrition is similar to the way that we learn about any other science, generally through observation and then testing these observations in the form of designed, planned experiments to determine a little bit more information about whatever it was that we observed. Some of the earliest nutrition research was going on back in the 1700s. And even prior to that, one of the classic examples of an observed phenomenon in nutrition was the disease scurvy. So when this country and this continent, rather, North America, as well as Central and South America, when these land masses were discovered, sailors were coming over from the European continent, and sailors and others on the ship started to notice that upon departing Europe, there were no issues or symptoms or anything of the sailors, but by the time they'd been several weeks at sea and starting to arrive over here on this continent, they had developed some pretty serious physical symptoms. Among them particularly was bleeding gums and just sores, particularly in the lips and the mouth and other areas of the skin as well. And so it took a little bit of time to figure out what was the cause of these bleeding gums and these just seemingly poorly intact skin cells anymore, such that they were kind of bruising or cutting easily and not really healing. So that we could call that an observation, just simply the observation that on long voyages at sea, sailors were developing these physical symptoms. And so from that, then scientists could, or even I could say early researchers, could just be curious about this observed phenomenon of bleeding gums. And so from that, they could develop what we might call a hypothesis. And the hypothesis is basically an educated guess about why this phenomenon is occurring. So at about the same time, these sailors, once they landed on the American continent, would notice that certain fruits would effectively heal these symptoms. Definitely certain things like cranberries and other tree fruits, whether it be peaches or oranges or grapefruits or even apples or pears. Upon consumption of these fruits, the sailors' bleeding gums would go away, any skin wounds or sores would heal right up. And so the hypothesis could be simply that lack of these fruits caused these symptoms that they observed, the bleeding gums and the skin sores. So then they could test the hypothesis in a variety of different ways, but that would effectively be, when we say test the hypothesis, we're effectively saying this is the research study. And we'll go through some examples of different ways to design a research study. And then in the research study, you're going to collect data, collect information based on how exactly you've formulated your hypothesis and how exactly you've designed your research. So then once you've collected enough data, you can analyze it, and from that draw conclusions. And then depending on what your conclusions were, you effectively have some new information, whether it refutes your hypothesis or supports it. And as goes in the scientific process, whether you got whatever your results were, you always retest and retest and retest. And the objective is to find through hundreds or even thousands of repetitions of a similar or even the same exact test, you wind up with the same exact results. So we'll go on the next slide and just look at a little more closely at how this process occurs. So just important to note that the scientific process is effectively how we know anything about nutrition. Anything that we take as fact or even as working theory in the world of human nutrition, we've discovered through the scientific process. We'll also look a little bit, we won't get too in depth in this course, but we'll look a little bit at how the scientific method, the scientific process is designed to help minimize any influences of bias by the researcher in terms of what they think is true or what they want to be true, certainly bias by any of the potential participants in the study, prejudice, and sheer coincidence. So ideally, the process is sound enough that all of these three potential confounders are ruled out or at the very least minimized. Here's the scientific process, another just depiction of it, but in a little bit more detail. So again, you always start with the observation, and then from the observation, you design your educated guess. And based on your educated guess, you can figure out what type of study design you want to establish. This having a control group and an experimental group we'll see is one type of study design, but they don't all have to have, any study type doesn't have to have a control group or an experimental group. So then in the experiment, this is where you are collecting your data, analyzing your data, and then drawing conclusions. And so the conclusions are effectively your results. And then your results are either going to support the hypothesis that you wrote, or they're going to refute the hypothesis that you wrote. So and you'll see either way, whether you get evidence that supports your hypothesis or evidence that refutes your hypothesis, you're going to go back up to this step of running the experiment again. The only difference is that if you have results that don't support your hypothesis, you're going to actually need to rewrite your hypothesis, because ideally your study finds evidence that supports your hypothesis, and then again, once you've repeated it enough times and have had other scientists repeat the experiment enough times, then you start to wind up with a pretty substantial body of evidence that supports whatever the original hypothesis is. And once you have enough of that evidence, then we start to develop scientific theory. And theory, eventually once we have enough evidence behind a given theory, we start to take that theory as fact. But as we've seen, for example, in nutrition, the ruling theory on the healthfulness of eggs seems to change every 5 years. So theory is just that. It's sort of it's the working theory. It's the best that we know. It's the most that we know, but it is not the same as fact. So that's a really important piece to just keep in mind as you go through this course, and certainly as you continue your studies and as you continue in life, is just recognizing that scientific research is at best just developing working theories, and we always have to be aware that those theories may eventually at some point be proven untrue. So in these next 2 slides, we'll just look at some examples of common study designs used specifically in nutrition research. So this is by no means a complete list of different study designs. It's a short list, actually. And if you look on your week 3 Blackboard page, I've got some optional resources that will further expound upon different types of study designs. So if you're interested, I definitely encourage you to check out those resources and see what else, what other types of study designs one could do. So these 3 on this page are all human studies. On the next page, we'll look at non-human studies. So epidemiological studies, effectively, we could consider these population studies. So looking at, generally speaking, epidemiological studies look at disease rates among population groups and compare different populations to each other. So the purpose of an epidemiological study is simply just to identify relationships. Epidemiological studies never are indicating what causes something else. So for example, going back to the scurvy example with the sailors, a really basic epidemiological study could compare the sailors to the people who stayed on the European landmass and just simply compared, okay, do the people on the landmass develop these same symptoms over the same course of time? And even without designing the study, we could have seen that they don't really develop scurvy. So that just starts to identify some related behaviors. So by being away from whatever is available on the European landmass, that's a behavior or a condition that relates to developing scurvy. So simply leaving the landmass isn't the cause of scurvy, but it helps bring more information to it. So it's effectively just finding more and more clues to, again, really help to solidify a solid understanding of what's going on. So epidemiological studies are often like the entry point or the beginning when new information or when a new observation or phenomenon is witnessed or discovered. Usually the first study would be an epidemiological study. And then as you gather more clues from your epidemiological studies, then you can go on and write or design some case control studies. So case control, as the progression might imply, is going to get a little bit more specific than epidemiological studies. So really looking at specifically individuals who have a common condition, or who have a specific condition, I should say, are compared with individuals who do not have the condition. So in the example of the scurvy, you might look at specifically just the sailors on the boat and see if there are any who didn't develop scurvy and compare them to the sailors who did develop scurvy. Or in more modern times, common case control studies might look at people who have type 2 diabetes compared to people who don't have type 2 diabetes, or populations who develop, or specific, not populations, but individuals who have developed cancer or who have had any sort of cardiovascular disease event, be it a stroke or a heart attack, and compare them to people who haven't. So again, the case control study is providing clues about the cause, the progression, and or the prevention of a specific disease, but still not suggesting or proving a cause and effect relationship. And then clinical trial is where we can start to get even a little more close to cause and effect. So clinical trials are also called intervention studies, because in a clinical trial, an actual intervention is used to determine how that specific intervention affects certain health parameters. So for example, in cardiovascular disease, you could apply, well, I'll back up. Commonly, clinical trials are used to test pharmaceutical drugs. That's the most prevalent form of clinical trial. So the intervention is always the drug, and you apply the drug to the population at risk or already expressing a condition, and you see if the drug helps alleviate the symptoms. So that's really where clinical trials are. But you could also, for example, use a clinical trial to test certain foods or to test a certain diet. So a great example is looking at the effect of a whole food plant-based diet on cardiovascular disease incidence. And this has been studied. And what the studies show is that when people follow a whole food plant-based diet, cardiovascular disease reverses. So the intervention is simply eating less processed foods and eating primarily or exclusively plant foods. And in doing so, anyone who already has a history of or is at risk for cardiovascular disease sees a reversal in their risk and a reduction in the events of cardiovascular disease. A clinical trial always has to have a control group and an experimental group. So whatever the health parameter is that's being tested, again, whether it's a CVD incidence or risk or expression of diabetes or, again, a type of cancer, the experimental group is the group receiving the intervention, and the control group is the group receiving either no intervention or oftentimes a placebo. So a good clinical trial would entail both groups already expressing whatever the health parameter or health issue is, because what you want to do is you want to compare very similar groups of individuals who are as similar as you can get them to be, and then test one group with your intervention and test the other group with just a placebo to see if the intervention has a more profound effect than the placebo. And then beyond human studies, there are also animal studies and cell culture studies. So animal studies are, as they would imply, they're studies done on animals. Could commonly rats or mice, but also could be monkeys, has been dogs in the past, rabbits is pretty common as well. So animal studies are usually used, again, kind of earlier on, like similar to epidemiological studies, but they're usually designed differently than an epidemiological study because you're not looking at full populations. You might be looking at a handful of rats. So these are used to provide very early data that can, and then the results of that data can then be used to design a human study. So typically animal studies are used when whatever the hypothesis is that wants to be tested would be considered unethical to perform on humans. So definitely brings up an issue of ethics. If anyone has interest in the ethics of animal testing, you'll see a lot of companies these days, like animal studies are common in any sort of topical treatment. A lot of skin products or shampoo products, hair care products, makeups are often tested on animals first to see if they have any adverse effects on the animals. So you'll see a lot of products will now say that they have not done any testing on animals for the growing population of people who has interest in animal welfare and animal ethics. In food and nutrition studies, again, oftentimes, pharmaceutical interventions would first be tested on animals. And then if there are no serious side effects, then they can go on and be tested on humans. And then cell culture studies, really just looking at almost sort of microbiology type study, but looking at just the cells in a laboratory. So not necessarily cells as they're functioning in a human, but you might have either taken some cells from human tissue or blood and cultured them in a laboratory, and then just study the cells themselves in the laboratory to see either what they do with a certain nutrient or look at various aspects of their metabolism or metabolic processes. Cell culture studies more recently, maybe the last 5 to 10 years, in the field of nutrition are particularly focused on nutrigenomics, which would suggest nutri for nutrition and genomics for our genome, but looking at the effect of certain nutrients on gene expression. So that's a common aspect of nutrition for which we use cell culture studies. So does a specific nutrient influence, promote, or inhibit specific gene expression? Okay, just want to go over a few terms that I mentioned in the previous slides and just give some specific definition. So an experimental group and a control group, again, we see this in clinical trials. Again, the experimental group is the set of study subjects, whether they're humans or animals, other animals, I should say. They're the ones being studied, and they're the ones receiving the intervention, whether they're subject to exercise, whether they're subject to a type of pharmaceutical drug, or whether they're subject to a specific type of diet, or whether they might be subject to a specific type of surgery, or again, even an exercise. And then the control group is the group who is very similar to the experimental group in every way possible. So generally having as many characteristics similar to the people in the experimental group reduce the risk of specifically coincidence. But the people or animals in the control group do not receive the intervention. So they are the standard of comparison for the experimental group. Nutrigenomics, we just looked at studying how different nutrients or different foods interact with genes and what that effect is on the person's overall health. Placebo effect we see potentially with control groups. So oftentimes, especially in a pharmaceutical trial, the control group might receive a placebo, which is an inactive substance that is indistinguishable from whatever the experimental intervention is. So again, commonly used in pharmaceuticals, because you could have the actual pharmaceutical pill, again, something that might be used to lower cholesterol levels or lower blood glucose levels. So there's an actual active drug. That's the intervention. And then the placebo would be a pill, probably just a sugar pill, but physically it looks the same as the drug. So the placebo is the way to make it so that the control group doesn't necessarily know they are the control group because they're still taking a pill. So they don't know whether or not that's the sugar pill, the placebo, or whether that's the actual pharmaceutical drug. And then placebo effect is when you actually see a change, so whether that's a physical or an emotional change that is not caused by necessarily anything other than the participant's mind or perceived expectations. So placebo effect is when you actually see an effect from the sugar pill, you're seeing an effect from the placebo. Double blind is when both the study subjects and the investigators or the researchers don't know the experimental group from the control group. So again, this further helps to reduce bias or prejudice in the research, because if you don't know who's getting the sugar pill or who's getting the actual drug, then there's a lot less opportunity to inadvertently input your desire or hope or preconceived bias into the data as a researcher or even as a participant. All right, so once the study is complete, then the researcher would publish their study, ideally in a reputable scientific journal. Prior to publishing the study, the experiment has to go through what's called peer review. So peer review is where other researchers or other scientists, ideally in that field, who have what we would consider expert knowledge on the subject, review the study very critically to help reduce the chance that there is any bias in the study or reduce the chance that it was faulty science, and basically just effectively raise the bar to make sure that only high quality research gets published. So if a scientific article does not get peer reviewed, it cannot be published in a scientific journal. And if it gets peer reviewed but it gets turned down, then the scientists either have to go back and correct whatever was erroneous in their study, or they may have to just start all over again. So best case scenario, the experiment or the study is peer-reviewed and it is accepted, then the scientists can publish their results in what we call a scientific journal, and sometimes we even call them peer-reviewed scientific journals. The purpose of scientific journals is really to communicate new information in that, whatever that field is, to other scientists. So in the world of human nutrition, this is, again, a short list, but some peer-reviewed scientific journals that you might find that are very reputable in the field of human nutrition. We have the American Journal of Clinical Nutrition, we have the British Journal of Nutrition, the European Journal of Clinical Nutrition, and Public Health Nutrition. Again, this is a very short list. You could even just Google peer-reviewed scientific journals, nutrition, and see what comes up. So I want you to refer back to this as often as needed, because certainly throughout the semester, certainly for this week's assignment, and particularly for your project, I do want you to be able to find peer-reviewed research from a reputable peer-reviewed journal. Last thing I want to touch on in the context of the scientific process is the issue of conflict of interest. So conflict of interest we could define as a researcher who has personal, financial, professional, political, or legal interests that have a significant chance of interfering with the performance of the researcher's ethical or legal duties in the field of science, or in the realm of science. So conflict of interest is basically saying, is this researcher publishing or coming from or receiving funding from or holding a job from some entity or university or establishment that might cause the researcher to sway the results of their study or publish misinformation so as to maintain their funding or maintain their faculty position or whatever it might be. So conflict of interest is a really, really important issue in scientific research. Typically, at the end of a scientific study, you'll see it will either state at the bottom, usually between the discussion and the references that they cite, you'll see either a section that says acknowledgements, or it might say other interests or potentially conflict of interests. So it can be written in several different ways, but it is required that scientists note whether they have any conflict of interest, so that again, the other scientists who might be reading this study or any professionals in the field who might be looking at or staying up to date on scientific research can have a chance to know, okay, well, there might be actually some bias in this research because the researchers state a conflict of interest. So that conflict of interest potentially would compromise the integrity of the research, and a lot of conflict of interest might in time undermine the public's trust in science. I wanted to list a few ways that companies who fund research might manipulate the study design or the publication of results. And usually this is happening so as to meet the purposes or the bottom line of whatever the company is. So we see this again, we see this a lot in pharmaceutical studies. Oftentimes pharmaceutical companies fund research. We do also see this in the food sector. So we've for a long time, actually for decades, we've been seeing massive food companies, food corporations, funding research to promote their product or to suggest that their product isn't as unhealthy as other research might imply. So we've seen this from the sugar industry. We've seen this from the egg industry, which is why there's constant back and forth. We see this from the dairy industry. And we've recently actually seen this from the cattle industry. Not surprisingly, there isn't really a plant industry, so there's not a lot of back and forth about the healthfulness of fruits and vegetables. Generally regarded as the healthiest foods for humans, no matter who's doing the research. So a few ways that massive companies who fund research might manipulate the research process. One is simply funding. So putting money out there to fund research that's only going to support the company's bottom line or end product. So again, if the product is milk, they're definitely going to publish research that suggests that bovine milk is necessary for the human animal. They might also publish research that suggests any other research that refutes the healthfulness of bovine milk to humans is wrong or erroneous. So they can design the studies in a specific way that would necessarily yield a desired result, or again, desired support of their end product. Again, you see this all the time in pharmaceuticals and pharmaceutical research. You can even see straight up lying, so falsification of the data, and or sometimes made up data. You could see the analysis and the interpretation of the data might be skewed in such a way that would again promote the company's bottom line. You might also see that companies will put a lot of money into challenging data that interferes with any information or that refutes any information that would challenge their profits. So if there's data out there that suggests that potentially milk isn't healthy for humans, that cow's milk isn't healthy for humans, then the milk industry would put a lot of information or a lot of money into challenging that data and suggesting that that is erroneous and false information. And again, the same would go with any pharmaceutical intervention. If it was ever published that, well, hey, a placebo had the same effect as this drug, that pharmaceutical company would put a lot of money into challenging the results of that study, because it would make them no money if people could just take a sugar pill and get the same results as their drug. And then companies would also suppress results. So not only just challenging opposing data, but also literally suppressing results that challenge whatever their bottom end line is, or challenge whatever research would support their product. So oftentimes this looks like the companies forcing researchers, well, first of all, seeking out researchers who are willing to sort of walk the line with ethicality in research. And then they'll fund these researchers to do research that will necessarily bring about data to support the company profits. And they will have the researchers sign a contract suggesting that the company has the right to review, delay, or even stop the publication of results, specifically so that if the results start to show anything antagonistic towards the company can just say, okay, we're throwing this out, we're not going to publish this. So conflict of interest is huge in the world of scientific research in nutrition and other fields. So very important to always check at the end of the study that you're looking at, do these authors state a conflict of interest?